Hey Thinksters, welcome to this video tutorial. So in this tutorial I'm going to address a very important conceptual topic in computer science, so in the area of computer science. So if you are interested in becoming a coder, then like there's no way around this topic. You may avoid the topic, but sooner or later it will come back if you avoid it too long. Okay, and so if you want to really become a master coder, if you want to reach a high level at coding, maybe earn like six-figure incomes or so, then you need to know the basics of this. It is asked in many coding interviews, like in the largest companies, Facebook, Google, Amazon. I've seen many coding interviews where the interviewers actually ask topics about this topic, about this area. So, and what is this area? It's the complexity, computational complexity, and in particular the big O notation. So you are going to learn about the runtime complexity of different Python operations, but also some conceptual stuff. What is the big O notation? What is the definition? How can you analyze your own algorithms, and so on? Yeah, and this is really a very important topic. So let's go ahead and dive into this topic. Good. So definition, the big O notation. In coding we have different operations, yeah, and the complexity of an operation or an algorithm, for that matter, is the number of resources that are needed to run it. Okay, so in what are resources in computing? So you have like the memory, and you have the CPU. Okay, so these are some resources. Time is a resource. So all of those are limited resources, and you can analyze algorithms with regards to their memory resource usage, with regards to their CPU usage, or even with regards to their expected runtime. Okay, and this is like the most important in many cases, the time complexity of an algorithm. And so we are going to focus on runtime complexity in this video, but so many concepts are actually are valid also for the other areas. So if you want to analyze your algorithms in regards to other resources, then many of this will actually hold for memory complexity analysis as well. And so why should you care? So what is the thing with computational complexity? So let's have a look at a very frequent operation, which is sorting elements. Okay, in Python, for example, say you have a list of some numbers, and now you call list.sort and you print the list, and if you run this you get the sorted list. Yeah, nothing unexpected. So 1, 2, 4, 14. But now it's important to see, so what is the best strategy to sort a list? And there are different algorithms that obtain the same objective. Yeah, different algorithms can sort a list. Like a naive sorting algorithm would be to, for example, so if you have a list of values 3, 2, 4, 8. Now a naive algorithm could take each element, this is called bubble sort algorithm, and move it to the right as long as this element is larger than the next element. Okay, so like this. So it would move it to the right until it reaches this point. Then it goes to the next element and it moves this element until it as long as it finds a larger element on the right. So it would not move the value 2. Then it would take like this next element 4. It would move it to the right as long as it can see it, but it cannot find any larger element. And then it would like move this element to the right. And so ultimately you would obtain a sorted list. But this algorithm has quadratic runtime complexity. So if you have n elements in your algorithms, in your list, then it will take you n squared operation on average. Yeah, so you will have like you need to compare each element against each other element in the list, and the second element you also need to compare it against each other element in the list, and the third one also. So you have like, if you have n elements, you need to compare n elements against each other element in the list. So you have n times n comparisons to run this algorithm. So this would be an inefficient algorithm. It has runtime complexity n squared for n elements which you put into the list. So in general, you can see you can measure an algorithm with a so-called complexity function, and the complexity function I would just show you simple complexity function of say these are 3 implementations of I quickly get rid of my face here. Okay, so these are 3 implementations of an algorithm, and here on the y-axis we see the complexity, on the x-axis we see the input of these the input size into these algorithms. Okay, so now we have 3 methods that accomplish the same thing. All of them sort a given list. But you see, with growing input, one method, this method, grows only slightly. Okay, so this is like the computational complexity. You can also view the y-axis as a runtime proxy. So this is like the runtime it takes, and of course, the more elements you have in your list, the longer it will take. In general, this is true for all algorithms that sort a given list. But some algorithms grow much faster than others. Some implementations accomplishing the same thing. And for example, here we have 3 implementations of the list sort function, and this one, this orange one, I guess, is with the thick dots. With the thick dots is actually much slower. Yeah, so it needs a lot more time, and it grows faster than the blue one, and the blue one also grows faster than this green one. Okay, so you have different implementation, different algorithms that solve this, and these algorithms they have different behavior with growing input sizes. So this is called the complexity function, and the complexity function, like we can have for n elements. So we measure it as a function of n, and n is our input size. Okay, so we have a function of n being our input size. And so for example, you can have different, so I will show you a table. So like your complexity function can look like this. Okay, so this is like the complexity function takes in n, which is the size of the input, and then it gives you a value, which is or basically it computes a function on this input size n, and this gives you the number of operations that are needed to run this algorithm. And you can create a complexity function for each and every algorithm you code. And here, for example, you see like this one is independent of the number n. So even if you have very large input sizes of a list, maybe the result would be like it would take only a second or so. So a constant number of operations. So for example, an example would be to give you to calculate the length of a dictionary. Okay, no matter how large the dictionary is, the length is stored in the dictionary. It has constant runtime, so it's very fast. Then you can have a complexity function like this. So this grows linearly, and with the more, so like if you go back here, so if you have the like runtime on the y-axis and the number of elements on the x-axis n, then a linear function would grow like this. Okay, so if you double the number of elements here, then you get double the runtime. And this is often a very good case if you find a linear runtime algorithm for problems, because then it doesn't grow too much. It doesn't become too hard, the problem and the algorithm. But then you can have problems like sorting. This one would be an example of sorting. It has n log n runtime behavior, and so it will basically take you more than n. So if you have like say 1000 elements, then it will take you 1000 times 10 logarithm of 1000. It will take you 10,000 operations. But then if you have 1 million operations, then you will have 1 million times the logarithm of 1 million, which would be like 1000 kind of. So you have like 1000 times 1 million. So you see this logarithmic factor grows also with a growing input size. So therefore this function would be worse than the linear runtime complexity, and an algorithm that has n log n behavior is worse than an algorithm that has linear runtime behavior, because it has it grows faster the more the larger the input size. And this is the purpose of the big O notation. Okay, you see in the big O notation you reduce term of the complexity, you reduce the complexity function to the largest growing term. Okay, so in this case we have like the largest growing term, it doesn't grow, it is a constant term, so therefore we have the big O notation, O of 1 function. If it grows like linearly, so if you add more and more elements to the to your complexity, if you add more and more elements to the input, then your complexity function grows linearly to the input size. So if you double the input size, the number of operations needed also doubles, and this grows, like the asymptotic growth behavior is O from n. Okay, so we have O from n, and this you will write it like On. And then if you have like sorting, for example, sorting algorithms are often so n log n behavior. If you have n list with input size n, then you have n log n comparison needed to sort a given list. And you can have like also squared complexity. You see, if you have if your complexity function looks like this, so you have n squared plus n, then this whole function will be dominated by this part of the equation. Okay, so for say n becomes larger and larger, then this part, this later part of the equation will have relatively less and less and less impact on the overall result of the function. Okay, on the overall runtime. So as the impact of this one shrinks with growing size n, your asymptotic growth, we say, is also n squared. Okay, so we just remove the terms that grow slower, that have a slower slope in growth. Okay, so we reduce the complexity function to its largest, highest growing term, basically. Okay, so this is a big O notation. It gives you, so you can quickly compare two algorithms. So say you have two algorithms. This is the first algorithm. This is the second algorithm that solve your problem. And now you can immediately see that both algorithms have the same asymptotic growth. Okay, because both have a squared growth, asymptotic growth in the number of input elements. Okay, so no matter what are the constant factors, even here the constant factor is like 100,000. It doesn't matter if you have very large numbers. Like if these numbers become 1 million, 1 billion, then these later numbers really doesn't play a large role. Okay, so it's just a proxy. So this asymptotic growth gives you a feeling about how good an implementation is for a given problem, so that you can compare different implementations and choose the one that has the lowest asymptotic growth. Okay, so now you have already a feeling about asymptotic growth and what it is basically, and how it works. And now you see that in Python different functions have different asymptotic growth. Okay, and so let's quickly go over the table. Sorry. Good. So here you see we have a table where like one column gives us the operation, another column gives us an example, and the third column gives us the computational complexity. And here you see like the index operation, for example, just accessing an element from a list with a simple indexing scheme has constant runtime complexity. So no matter how large the list is, so even if the list has 1 million elements, it just takes you like one operation, one split second. So it doesn't really grow with the number of elements. So even if the list grows and grows and grows, it takes always the same time to access this element. And also to store an element with lists is very efficient. Measuring the length of a list, the length is just a property on in a given list, so you can simply return the property, and this has constant runtime complexity. So no matter how large the list grows, it has the same number of operations, so the runtime complexity is constant. And this is true for many operations in Python lists, like appending stuff, popping stuff from the end, like from the head of the list or from the tail of the list, and clearing things. But then there are some operations like slicing. Here you slice from start index A to stop index B excluded, and this has like the complexity of this operation is depends on your choice of your size of the slice, basically. Yeah, so the size of the slice interval. If the slice is very large, then the complexity also grows, but if the slice is smaller, the complexity stays constant. Then you have the extend operation. The extend operation adds a number of elements stored in L2 to the list, and it's like the complexity is the number of elements in the first list plus the number of elements in the second list. And also you have the constructor, for example, with list. To create list, the runtime complexity is proportional to the number of elements in the list you want to construct. Then you can check for equality, like if you have two lists and you want to see whether both elements in the list are the same, then it takes constant number of operations. Yeah, so if you have like two lists, 1, 2, 3, 1, 2, 3. Now you need to check for the first elements, you need to check the second elements, the third element. So you touch every element once, basically. Okay. So therefore, equality has like a linear runtime complexity. And of course, if the lists become larger, you need to touch more elements to find to find whether two lists are equal or not. So they may differ only in the last element. So you need to check all elements before whether they are equal, and only then you could return false if you went all the way to the right and found that the last element doesn't match. Good, then you have like linear runtime complexity for operations like slice assignment, deletion, removal, membership, so checking whether an element is in the list. You need to go over all elements in the list in order to find whether this element exists. So for example, if you want to check this list, this list below, whether it contains element 3, you need to check the first element, no, yes. Okay, and then you return yes. Or if it doesn't exist, you need to check it and return no. But you need to check all elements in the list. So therefore, runtime is linear to the number of elements in the list. Next, you need to, so if you copy the list, it takes you also linear runtime comparisons there. So you need to touch every element to copy this list, basically. Yeah. So you need to copy the first element, copy the second element, copy the third element, and so on. So you need to copy all elements in the list. You can pop the first element of a list, and also this takes you linear runtime complexity. Many don't know it. Why? Yeah, because it's like lists are implemented with arrays. So if you remove the first element, then you need to shift the whole array. So you need to shift the whole list to the left, and therefore you have to touch each element and copy it in the worst case. To find the minimum or maximum of the list also is linear runtime, because you have to go over each element. So you need to check the element, and you like store in a temporary variable, you store the minimal element you have found or the maximum element, and then you check the next element. If this is smaller or larger than the other one, then the one you have stored, then you just replace it. Otherwise you move to the next, and so you go through the list and always keep track of the minimum or the maximum element. So therefore it has linear runtime complexity. Also operations like reversing the list or iterating over a list has linear runtime complexity. Now sorting has n log n runtime complexity, so it's worse than linear runtime complexity, but it's better than the quadratic sorting complexity we have seen in the beginning of this video. Okay, so like these are the different operations of the different Python operations. Now you have at least a feeling about the runtime complexity of those operations. And now let's go into Python sets. Python sets have similar operations like lists. You can measure the length, you can add elements, you can remove elements, but there are like two highlights which I want to show you. Like first of all, checking whether an element is in a set is now only constant runtime complexity. So it doesn't have linear runtime complexity, and the reason is that sets are implemented with hash tables, and hash tables allow for very quick checking of the membership. So basically, you have you take an element, you hash it you have a hashing function that hashes this element to a certain integer number, and then you can quickly look up whether like this integer number is in the set. And there's a very smart implementation with hash tables. So you have a table of hashed elements, basically already stored as an array, where you can quickly look up whether an element exists in a set or not. And if it exists, and yeah, you can do it with constant runtime. So no matter how large the set is, even if the set has 1 million elements and 2 million and 3 million and 4 million, it will always take the same time to check whether an element exists in a set. So membership is much better for sets than for lists. And like one of the logical reasons for this is that sets have so lists are more powerful than sets, and you need to buy this power with computational complexity. Kind of think of it this way. There's no free lunch, so they are more powerful. Why? Because lists allow for ordering of the elements, while sets are unordered collections. So you lose the ordering information of some elements, and this allows us for an efficient implementation of the membership and also of removing of elements. But of course, we have like less powerful behavior. We need to get rid of some things, like getting the ith element of the sequencer. So it doesn't work for sets because sets are unordered. So there is no ith element. You can only remove a given element or so, but you cannot get the ith element in the order. Okay, so therefore, like membership and removal is faster, but we buy this kind of with less powerful operations, less powerful data structure. But oftentimes it's sufficient to take a set data structure. Even if you need to check membership very often, then you should prefer the set data structure if possible. If you don't need the ordering. Dictionaries are also like you can access some keys and values of dictionaries, override, so store new values in dictionaries, check the length, delete elements from a dictionary, clear the dictionary. All of those operations have linear runtime. Only iterating over a dictionary and creating a dictionary has linear runtime in the number of elements. Okay, so now you know for like one Python statement, you know the computational complexity. So for example, if you have, let's go here. Okay, so let's consider this example where I will give you a whole example. So here you have like 5 lines of code. Okay, so first you create a dictionary where you map the keys to values, and the values are lists. Yeah, so for example, so each key stores a given list as a value argument. Then you get the first element, the element with stored associated to the key 1, which is like this whole list. You get this list, you sort this list, and then you print the result of the list. Okay, so this is a very simple algorithm if you want. Okay, and an algorithm just means multiple lines of code. And now we have explored the runtime complexity of different accessing different data structures. Okay, here we create a new dictionary, so we know the runtime complexity of this operation. We know the runtime complexity of getting an element from a dictionary. We know the runtime complexity of sorting and of printing. So now the question is how to compute the runtime complexity of a more complicated code snippet. So if you know the runtime complexity of a single operation, then it's very easy to calculate the runtime complexity of a whole code snippet. Yeah, so how do you do this? Basically, you break up your code into, so like really, so you have now operation 1, which is like dictionary creation. Now we have to look up in our table, and we see that dictionary creation has linear runtime complexity. So if you create a dictionary with n elements, the runtime complexity is linear, so it's O from n. And then you check the second operation. It's indexing, so like dictionary indexing. And we know this has constant runtime complexity, so no matter how complicated, so how large the dictionary is, it takes us only a constant number of operations, like very quickly. Even for dictionaries with 1 million elements, we simply need one operation. Then you check the third operation, like sorting a list. And sorting a list, you know, is like n log n. So we have with n elements. In our case, we have 4 elements in the list, so we have like 4 log 4 operations to sort the list. So it will be quick, yeah. But I mean, we could have an input that is larger. We could have lists that are larger. So what if the list has like 1 million elements, and we want to analyze this algorithm for all possible inputs? Yeah, so this could be a function that takes as input certain lists, and we want to compute, like sort the first list of the dictionary. So now this algorithm depends on the input size. If the lists become really large, we want to analyze how does this algorithm behave. And now the fourth operation is to print the list, and to print an element, a list with n values, like take something like more or less linear runtime. No, not more. It has exactly linear runtime behavior. Okay, and so and now you know the individual operations. How can you compute the runtime complexity of the overall thing? Yeah, so you simply, so let's do it in the code. So we already know, like, so we simply add them together, right? So because we need to execute in a code statement, we execute the first line first, then the second line, then the third line, so the fourth line. So if we need to wait O(n) time, then we need to for the first operation, and O of 1 time in the second operation, then we simply add them together. And we do this for the third operation and also for the fourth operation to obtain this equation. Okay, and now you see this equation consists of 4 parts, and basically now there is a like chain rule for the big O notation, where you can chain those operations together. So if you have like this this equation, you can simply first add together the complexity of the individual operations, and only then you basically reduce it to the big O notation. And now you see, if you rearrange those terms, then you see and you sort the terms like by complexity, it looks like this. We have n log n plus 2n, because we have like 2 times linear runtime behavior, plus 1. And now we have an interesting step, which is to get rid of all slow growing terms, basically. Yeah, so because in this equation we can consider them separately, we can look at them separately, and you see that this part here is the fastest growing part, so n log n. If we increase the size of n, so we add more and more elements, then this part will dominate the whole equation. Sooner or later, this part will take the longest to execute. Okay, and what is this part? It is the sorting part. Okay, so this one operation, sorting, will dominate the rest. So if we want to optimize our algorithm, then we should start optimizing here. Yeah, so because this is our largest leverage point, it's the slowest operation, and therefore our the runtime of the overall thing is asymptotically restricted by this term. Okay, so it grows like this term, more or less. So of course we have we add this 2n, but this 2n will be later dominated by our n log n term, and therefore we can reduce it. Yeah, so we simply get rid of all slow growing terms, and we only remember the fastest growing term, and we throw everything else away. And yeah, in this way you can analyze an algorithm. You can figure out the big O notation of any algorithm you want by simply breaking it down into its constituent parts, and then adding them together with this chain rule, as I did here. And you can even do this for if you have like for loops or while loops, and then you need to figure out how often do you execute the loop body. And so say if you would have a loop that executes k times, and the complexity of your loop is like f of n, then your overall runtime would be of course k times f of n. Okay, so you k times the complexity of the loop body. Okay, so this way you can figure out the computational complexity of your overall algorithm. You can quickly analyze it by breaking it, by figuring out the complexity of the individual parts which you have learned previously, and simply adding them together using this chain rule notation. Okay, so thanks for watching this video. It was a quick introduction into how to analyze your own code, regarding computational complexity, and what is the computational complexity of different Python operations. And yeah, if you like this video, then yeah, check out more videos from Thinkster. Thanks and see you in the next video. Bye.